Welcome students, we're covering section 6.3 today. We're going to find volumes of different solids. First up we're using the general slicing method. So let's see what it's talking about as far as theory goes. I have sliced this solid into n number of sections, and if I find the cross-sectional area of each slice multiplied by the width and then add each of those volumes, I should get the volume of that entire solid. And if I keep slicing it so that I have an infinite number of slices, that means that the width goes to 0. So let's look at what we have mathematically. I have the area of each cross-sectional piece times the width. Adding up all of those pieces should get me the volume. And if I make those slices so thin that the width goes to 0, meaning I have an infinite number of slices, what that is equivalent to is the integral of the area times the width of each slice as that width goes to 0. So that's our general theory of what's going on. Now let's try to work some problems with this. First up, I have a solid, and it's bounded by this y equals, here's my 2 minus x squared, and this is the just plain x squared. Alright, so it's bounded by, and I have to imagine this being a solid, and it's also has as its base the xy plane, so it's kind of flat on the bottom, and then it extends outward with these two functions being its bounds, what's holding it in. So I need to find the area, and they tell me that these are semicircular discs, if I can imagine how it's projected outward. So the area of that semicircular disc is going to end up being 1/2 pi r squared because they're semicircular discs. So my next order of business is I have to find the radius. And the radius would then be, if I look at what the distance between these two right here, it's going to be half of that distance. And so it would be half of that distance, and that distance is the 2 minus x squared, and then the bottom side is the minus x squared, and that would get me the radius of that each of those discs. So doing the computation on that, I would end up getting 1 minus x squared. Plugging in here to my area, I'll just go ahead and plug into volume, I guess, might as well. And you'll have to find these intersection points. Just solve this for where they set them equal and solve for where they intersect. You can also do that with the calculator, and you'll find that this is at 1 and -1, but you do have to perform that task as well. And then it's going to be 1/2 the area, which is 1, and then the radius 1 minus x squared quantity squared dx, and then I'm going to do that integral. The easiest way to do that integral is just multiplying it all out and getting the integral of 1, -1, and I'll just go ahead and pull the 1/2 pi out here, and then that's going to be 1 minus 2x squared plus x to the 4th dx. And if I do that computation, I'll end up with 8 pi over 15. There we go. That's the first one. Next we're going to talk about the disk method, and we'll use that quite a bit. In this we have some sort of region, and let's just say it's bounded by this function x plus 1 quantity squared, and it's bounded on either end by x equals 0 and x equal 2. Now what I'm going to do is I'm going to rotate this region about the x-axis. Rotate it about that x-axis. And when I do that, I'm going to create a solid. And I'd like to find the volume of that solid. Well, what this is talking about is it's saying that your volume is, you've got to get that surface area, and that surface area is going to be pi r squared, because that's the surface area. And using that same slicing technique times the thickness, so do you see that it's the pi r squared, because my radius here is just that function. And let's look at what the textbook has for you after you have rotated it, just so that you can get a better idea of what this looks like visually in your head. Notice that it has been rotated about that x-axis, and then they filled it in with the solid there. So let's see if we can work their problem. I know that volume equals, and I've got to find the limits of integration. Oh, that was pretty much given to me by the restrictions, the bounds here. So it's from 0 to 2. And then it's going to be pi times the radius, and the radius in this case happens to be the function, so it's that radius squared, x plus 1, quantity squared, and then dx. Oops, and I have to square that square. Sorry about that. There we go. And then what I'm going to have is from 0 to 2. Let's pull that pi out, because he's just a constant anyway, and then it's going to be x plus 1 to the 4th dx. Reviewing our substitution, that's the method I'm going to use for integration. Let's let u equal x plus 1. Then du is just plain dx. That makes it really handy. I'll have pi 2 to 0 u to the 4th du. I like integrating that. Pi u to the 5th over 5, with the limits of integration in that case, well, they wouldn't exactly be 2 and 0, so let me fix those. Let's see, it would be, if x is 2, that would be a 3, because u is x plus 1, so my limits here are going to be from 3 to 1. And then just plugging this in and computing. Alright, there's my arithmetic. And on to the next one. The washer method is an extension of the general and the disk method. In this particular case, I've got a function on top and a function on bottom, and I'm going to rotate this about the x-axis. I'm going to create a solid, in this case, that has a hole in it. And you could do this by the disk method. You could find it revolved about from the top and then just subtract out that hole, which is basically what they're doing. They're just saying that the radius here, because it's pi r squared, still have some sort of circle or some sort of circular surface here, so it's pi r squared, but my radius is the top one, the top function minus the bottom function, because it has a hole in it, and the hole is created or generated by this bottom function, so that's why it's being subtracted out. So let's get right down to it. Volume equals, and I'll need to know exactly what this point is and what this point is. You'll need to find those intersection points. I've already found them, 0 and 1. You can do that with your calculator. You can do that algebraically. Get a numerical answer if you do it with the calculator. But I'll need pi, and then I need the top function. It's not necessarily f, it's the top function minus the bottom function. And the top function in this case is square root x, quantity squared, minus the bottom function, which is x squared quantity squared dx. So I'll do the algebra. Alright, I went ahead and integrated. It's a pretty straightforward example, and when you plug this one in for each of those and then subtract off the 0, you'll end up with 3 pi over 10 as the volume of this solid that is created. And I put this picture down here so that you could see. You have to imagine this as a solid as it goes outward. It's a very visual section. You have to imagine what things look like as they're rotated about different axes. We're going to perform these same techniques, but we're going to do this now about the y-axis. And the first one wants me to revolve this about the y and then compare the solid that's generated when I rotated about the x-axis. So I'm going to rotate this solid this way about this y-axis. And in this case I'm going to be looking at this outside function minus this inside function in my creation of the bounds. I went ahead and got the intersection points, and my volume is going to be equal to, now I will be using, because there's an empty spot here and I'm not rotating it about just the straight well, I am rotating about that axis, but I have a hole here, so it will end up being the washer method, because there will be an empty spot in there that needs to be subtracted out. And my limits of integration, I'm integrating about the y, so my limits of integration are up and down, so this would be from 0 to 2. And then I've got pi, and then my outside guy is 4y quantity squared minus the inside radius, which is y cubed quantity squared, in this case dy. And then we'll just do that integration and see what we get. Cheat problem in that they wanted me to rotate it about the y and then rotate it about the x, so I have to do two problems in one. So here I am, I'm going to rotate this now about the x-axis. So I'm rotating this, creating a solid as I rotate it about that x-axis. And this is actually how I plugged it in on my calculator. I actually plugged in x to the 1/3 and 1/4 x so that I could get this graph. My volume is going to be, since I'm rotating it about the x and creating this washer in this fashion, my limits of integration are going to be from 8 to 0, because this is going to be with respect to x, pi. My function that is on top in this case is the x to the 1/3 quantity squared minus the bottom function is 1/4 x quantity squared dx, and then I'll do that algebra and probably a little bit of the integration. Okay, when I do that integration, when I do that little algebra there and then I do my integration, I get 128 pi over 15, and then I compare the two and they want to know which one is bigger, and it would definitely be this one, so it would be when it is revolved about the y-axis. Volume is greater. And that's it for section 6.3. It's going to be a lot of practice. Just think about the top function minus the bottom function when you're dealing with the washer method. And if you have any questions, come see me at the Collaborate. And thank you very much.